welcome to my talk on electrokinetics of polymeric fluids in narrow rectangular confinements. It's a research paper authored by me and Professor Udito Ghosh, and I'll be presenting it. Now, here is the problem statement. We have a long rectangular channel in which a fluid is flowing. Now, the fluid has electric charges disordered in it because it has an electrolyte which has dissociated. Now, the positive charges settle on the walls, and the bulk of the fluid is left negatively charged. Also, the negative charges flock towards the walls because they're attracted by the positive charges, and we get to see an electrical double layer. And the layer the closest to the wall is called a stern layer, and we assume that it has a known electrostatic potential of zeta star. Now remember that whenever you use star for a quantity, it refers to a dimensional quantity, and non-dimensional quantities are written without a star. We have chosen this convention because we'll be predominantly working with non-dimensional quantities. Now let's look at other aspects of it. We may or may not apply a pressure gradient, and we have chosen the characteristic scales as shown on the slide. For example, the pressure-driven velocity of a fluid is chosen as the characteristic velocity scale here. There are some dimensionless quantities that come out when we non-dimensionalize the equation. For example, you have the ionic Peclet number, which shows how prominent is the advection of the charges over diffusion. Then we have kappa, which shows how large is the channel height with respect to the Debye length. And Debye length is the length over which the effect of the charged walls significantly drops. Other numbers are the Deborah number, which tells how large is the relaxation time of the liquid as compared to the time scale of the flow. Then you have the aspect ratio, and then you have the Dawkins number, which tells us how conductive is the stern layer as compared to the bulk of the fluid. Now here are the governing equations. The continuity equation, which is essentially mass conservation. Then Poisson-Boltzmann equation, which tells us how the electrostatic potential is distributed. Then the XYZ momentum equations. Now we have two currents flowing through it. First is the streaming current. When charges flow along with the fluid, it amounts to an electric current called the streaming current. Now, if an electric field is present across it, it leads to conduction. If an electric field is not present, then the current should be zero, right? So when a charge is flowing and thus causing a streaming current, a potential gradient is automatically developed across it, which sends the conduction current in the opposite direction. And this automatically developed potential gradient is called the streaming potential. Now, fluids are non-Newtonian, so we use two models to describe their behavior: the simplified exponential Farnthian-Tanner model and the Gauss model. Now, here are the results. One interesting result is that in Gauss model, the flow cannot be strictly unidirectional. If we try to make the fluid flow in one direction, it invariably circulates as we have shown here. Other important results are these. For example, we have plotted the average velocity with increasing aspect ratios, and the dotted lines in both the graphs are the velocities of flows of all parameters same, except that those flows are in parallel plate channels. As aspect ratio increases, our velocities approach those. So we can see that as the Deborah number increases, the parallel plate channels are becoming worse approximations of the rectangular channel, which means rectangular channel analysis is more important over there. Finally, here are some more graphs. It tells us how the streaming potential is gained due to the shear thinning of the fluids, and we plot that for various parameters here. For example, here we have chosen to vary epsilon and A. Epsilon is a non-dimensional parameter in the Farnthian-Tanner model, and A, which is called the mobility factor, is a non-dimensional parameter in the Gauss model. We also choose to vary the size of the parameter kappa, which means we go from thick or rather thin EDLs to thick EDLs, and we show how the streaming potential varies across that also. So this summarizes our results.